Hi, everyone. My name is Priya Donti, and I'm a PhD student at Carnegie Mellon University, co-advised by Zico Coulter and Dinesh Azevedo. And today, I'd like to tell you a little bit about my work, bridging deep learning and electric power systems. So my work is fundamentally motivated by the issue of climate change. Climate change is, of course, one of the most pressing issues of our time. And in order to address it, we'll need to make deep cuts in greenhouse gas emissions over the next decades. My work specifically takes a look at reducing greenhouse gases in the electric power sector, which contributes about a quarter of global emissions. So strategies to reduce emissions in the electric power sector, I might call this decarbonizing the electric power sector, have two main parts. The first is to increase the efficiency of the power system, so we fundamentally use less power. The second is to transition away from fossil fuels and towards low carbon sources of energy like solar, wind, and nuclear. A challenge, though, is that sources like solar and wind are variable, which means that the amount of power output you get from them depends on external factors like the weather. This means that power grids need to be optimized at increasing speed and scale as more variable generators get put onto the grid. So addressing this challenge will need lots of different tools, technical and non-technical. But my work has looked specifically at where machine learning can play a role. For instance, this figure on the slide, which is from a paper called Tackling Climate Change with Machine Learning, written by myself, CSGF alum Kelly Kachansky, and a host of others. This figure shows various ways in which machine learning can play a role in decarbonizing electric power systems. So this includes things like forecasting the power produced by renewables, speeding up electric power system optimization, detecting methane leaks in natural gas pipelines where methane is a really potent greenhouse gas, and even accelerating the search for new clean energy materials. And while a lot of these kinds of applications are being implemented on the ground today, there are also lots of places that need innovation to kind of surmount various practical and methodological challenges. For example, one big challenge is that machine learning methods are traditionally very bad at satisfying physics and hard constraints. And in power systems, this is a deal breaker in many cases, since failing to satisfy the physics of the power grid could lead to blackouts. My work looks at addressing this challenge in the context of deep learning through the use of a technique called implicit layers. So before I dive into implicit layers, I want to step back and give a little bit of background on deep learning and neural networks. So you might have seen different depictions of neural networks in different places. For instance, as a black box in which you put some inputs and get some outputs, or this traffic lighty representation, kind of a bunch of circles connected together by a bunch of lines. But maybe opening up the black box just a little bit, one way we can view deep learning is basically just as differentiable function composition. Basically, a neural network is just a bunch of functions or layers composed together, where these layers have a couple of different properties in general. So the first is that most of them are nonlinear. That's what makes the neural network learn complicated functions. The second is that these layers have parameters. They're parameterized. So you can adjust some kinds of parameters to change the overall function represented by the neural network. And the third is that they're differentiable. So you can take derivatives of each layer with respect to its parameters and its inputs. So a deep neural network is just a neural network that has lots of layers composed together. That makes it deep. The goal in general is then that you want to adjust the parameters of the neural network so that the overall function it represents is good. And you generally do this by putting some inputs into the neural network, getting some outputs, and assessing some loss or error function on those outputs. What you then do is you calculate the derivative or the gradient of your loss function with respect to all of the parameters. This is known as backpropagation. You then use that gradient information to update your parameters. And then you rinse and repeat this whole process. So your standard neural network has, a standard set of the kinds of layers that tend to be used. So you might have heard terms like ReLUs and sigmoids and convolutions and so forth. But recently, there's been a lot of interest, particularly within the optimization and scientific communities, in figuring out, can we expand the notion of what a neural network layer is? So can we expand the set of functions that we can actually use as neural network layers? And the answer is yes. A lot of recent work has looked into creating what are called implicit layers that can represent things like ordinary differential equations, or physics, or optimization problems, or logical reasoning. Briefly, these kinds of layers are called implicit layers because they represent implicit functions, so functions for which you need to use an iterative method like Newton's method to get a solution. And they use something called the implicit function theorem to efficiently compute gradients through these functions. While some of my work has focused on how you create implicit layers, like that bottommost paper you see on the slide, what I'm going to dive a little bit more into now is ways that you can actually use these implicit layers. At a high level, by having this toolbox, by being able to embed implicit functions like physics and optimization problems into neural networks, we can all of a sudden do a lot of cool things, like, as I motivated at the beginning of this talk, enforce hard constraints within electric power systems workflows. So I'm going to give one example of some of my work using implicit layers to enforce hard constraints in the context of control problems in electric power systems. Control problems are problems where you have a system, like a power system, that has some state, and you take some action on that system in order to affect the state. And there are two general philosophies about how you actually go about picking actions on a control system. One philosophy is that you want to take actions that are as good as possible with respect to some performance metric. You want to maximize your overall performance. This is the view that's used by the area of reinforcement learning, which is a subfield of machine learning. And it generally works well for systems where you want to do well on average, sort of when averaged across all of the different times that you're acting on the system. But it's okay if the system fails every now and then. So for example, if you're using reinforcement learning to play some kind of online game, it's okay if you lose sometimes. For other systems, though, failures are unacceptable, and failures can have catastrophic consequences. So for instance, if the control systems and the brakes in your car fail, that could lead to an accident. Or on the power grid, a control failure could lead to a blackout. So in these kinds of settings, you want your controller to perform well, sure, but more importantly, you never want it to fail. So this is the view adopted by the area of robust control, which tends to pick simple controllers that perform okay, but will provably make it so that the system never fails. So the question we address in this work is, can we create a method that performs well, like reinforcement learning methods do, while also provably guaranteeing robustness, like in robust control? To address this challenge, we let our policy, or our way of picking actions, be represented by a neural network. So the naive thing to do here would be to feed our state, X, through the neural network, and let the output of the neural network, U tilde, be the action we take. But the issue is that this initial action output by the neural network has no guarantees on it whatsoever. So we take advantage of the fact that we can embed nice implicit layers into neural networks and insert a sort of robustness enforcement layer. Basically, for every state X, we derive a set of actions that are provably robust at that state. We then project our naive action U tilde onto this set of provably robust actions. And then we get the actual action that we're going to take, which we're calling U hat. We then figure out how good this action is by getting some reward when we act upon the environment, and we adjust our neural network accordingly. Importantly, since our projection, since this robustness enforcement layer is differentiable, it's visible to the neural network as it's learning. We can take it into account when we adjust the parameters of our neural network, and this is overall a good thing for the performance of the neural network. So just for completeness, for those who are wondering how we obtain this safe set of actions we project onto, so briefly, like in the field of robust control, we impose some kind of uncertainty model on the dynamics of our underlying system. We also obtain a Lyapunov function via robust control that can be used to verify the stability of the system. You can think of a Lyapunov function kind of like a potential function. High values mean your system is farther from equilibrium, and low values mean it's closer. So given this uncertainty model and this Lyapunov function, the idea is that if we can sufficiently decrease our Lyapunov function by enough at each point in time, then the value of this function will asymptotically decrease to 0, which means we've stabilized our system. So what we do is that at each time step for the state that we're currently at, we derive a set of actions that are guaranteed to decrease our Lyapunov function by enough, even under worst case uncertainties in our dynamics. For the systems and Lyapunov functions we look at, these end up being convex and non-empty sets in U, which means projecting onto them as a convex optimization problem, which we can differentiate through. So if you got a little lost there, no problem. But the high-level takeaway is that we can derive some safe set of actions and then project some preliminary action proposed by a neural network onto this safe set in a way that's visible to the neural network during learning. We test this method out on a few different systems, including a synthetic microgrid system in our paper. So just to show some illustrative results on a synthetic system, this slide shows the performance of our method, the last 2 columns, against a variety of non-robust baseline methods, first 3 columns, and a robust control method in the middle column. We show performance in an ordinary case in blue, where the system operates as usual, as well as an adversarial case in orange, where we pick system disturbances that are maximally destabilizing for each method. Overall, what we see is that our methods improve in terms of average case performance with respect to the robust control method. Lower values on this plot are better. So we improve with respect to average case performance compared to the robust control method, while, unlike the non-robust methods, actually staying stable in the adversarial case. So our method performs well and yet is provably robust. So what I talked about in the last few slides was one example of a benefit we can get from including implicit layers in neural networks, so enforcing hard constraints. In addition to the robust control setting we talked about, some of my other work looks at how we can use implicit layers for constraint enforcement when we're approximating optimization problems using neural networks. But there are other kinds of things we can do as well. So for example, in the setting of forecasting, a lot of forecasting models are used to inform some kind of decision, and many decisions are represented by optimization problems. So we can actually use implicit layers to create decision cognizant forecasts by embedding knowledge of the optimization model into our forecasting method. We can also use implicit layers to embed physics-based quote unquote inductive biases or assumptions about our underlying system into deep learning models. So in the same way that convolutional layers in deep networks encode assumptions about images, we can use other kinds of layers, implicit layers, to encode assumptions about other kinds of scientific systems. So more broadly, given that most of us are computational scientists that work in some scientific domain, one thing to think about is when you use machine learning or statistics or some data-driven method, what do you wish it were that your data-driven method knew about the physics of your underlying system? So for example, are there hard constraints that you wish it could enforce? Is there other kind of system knowledge that you wish your method knew about? Implicit layers might provide one way to think about actually embedding that scientific knowledge into your data-driven methods. So that's the end of the technical part of my talk. But before closing, I want to take a minute to say thanks. Being a CSGF fellow has just had an immense impact on my PhD journey in so many ways, and I'm really very grateful for that. To give a few highlights, during my fellowship, I got to do a practicum at the National Renewable Energy Lab. The work I did was in some ways, off the track of my main dissertation work. I was doing a project on matrix completion, which has nothing to do with deep learning. But it was an awesome opportunity to dive further into traditional power systems problems. The knowledge I gained there definitely shaped the rest of my PhD. And not to mention, I got to work with some brilliant collaborators and make some great friends along the way. CSGF also gave me the freedom to do things a little bit off the traditional PhD path. For instance, during the PhD, I co-founded Climate Change AI, an initiative that aims to foster impactful uses of machine learning to climate change. It's been amazing to see CCI flourish over these last few years, with thousands of researchers and practitioners and policymakers from around the world participating in CCI's activities and network. I'm so grateful for CSGF for giving me the freedom to build something like this during the PhD. And finally, I'm just immensely thankful for the CSGF community. Both within and outside of program reviews, it's been truly an honor to learn from you and grow with you and generally feel like I'm part of one big CSGF family. So again, many, many thanks, and I look forward to taking your questions.